All right, it's 2 o'clock. So this is the time domain astronomy session, and I'm the session chair. My name is Mick Killick. I'm at University of Oklahoma. The first speaker is Keaton Bell, and he will tell us about the search for planets transiting white dwarfs from APO. Go ahead, Keaton.
Okay, sorry. Figure out how to unmute. Thanks, McCremon. I want to tell you all a bit about my ongoing campaign to confirm candidate transiting planets orbiting white dwarf stars with the APO 3.5 meter. This project is the focus of my NSF AAPF fellowship. So for quick context, a little stellar evolution review slide. Only about 2% of the most massive stars turn into black holes and neutron stars at the end of their lifetime. So in my opinion, that's like negligible. Brown dwarfs are not legitimate as stars, and black dwarfs aren't really real. So to first order, my first overgeneral characterization is that pretty much everything ends up as a white dwarf at the end of its lifetime. And then a little bit of exoplanet context. Pretty much all stars have planets as the takeaway. This graphic shows in red there's a higher likelihood of exoplanets in a radius and orbital period bin, and for F, G, and K stars, if you sum over all this, pretty much there's tons of planets out there. So if you take these two overgeneral statements, there's lots of planets, most stars become white dwarfs, and you mash them together, you kind of get this suggestion that most white dwarfs should host planets, or at least remnant planetary systems. But that doesn't mean they're easy to find. There's some additional observational evidence that planets are, or at least planetary remnants are common around white dwarfs. One is that about 25 to 50% of white dwarfs have metal pollution in their atmospheres. Because white dwarf gravities are so high, metals should quickly sink below the photosphere and not be observable in the spectra. And so the fact that we see metal pollution so commonly in white dwarf photospheres means that there's an ongoing accretion process that, and this is interpreted as planetary remnant material being accreted onto white dwarfs. Another line of reasoning to suggest that there is planetary material around white dwarfs is an infrared excess detected around like 2% of white dwarf stars, probably suggesting that there are planetary debris disks around these white dwarfs, like this little kind of cartoonish graphic from Spitzer shows. This there's probably a lot more debris disks out there that just aren't detectable as infrared excesses. And then finally, we've started to discover some systems of transiting planetesimals, like disrupted planets and planetary material transiting white dwarfs, and even evolving dynamically over many observed transits. Here's some high-speed photometry light curves from my thesis work showing that the transit shapes and properties vary over sequential days in this sort of 4.5 hour near the Roche radius material around this particular white dwarf. This was discovered in K2 data. So this is all just a backup that white dwarfs are likely to host planets. So let's take a look at what that might look like. Starting first with the more common like Sun-Earth system. If an Earth-sized planet transits a Sun-sized star, it probably only creates a transit signature that has a depth of about 100 parts per million, and detecting something like this requires precision photometry from space. You've got to use like Kepler or TESS to hope to find any signature this small in the light curve of a planet-hosting star. But if I take this one solar mass main sequence star and replace it with a one solar mass white dwarf, then we have a bit of a problem, because we don't get transits anymore. The white dwarf's just too small to transit. And this is the reason that these transits are so difficult to find, because the inclination has to be so perfectly aligned with our line of sight in order for any transits to occur. So I'm just going to square this up a little bit and zoom in on a transiting system. The blue dot here is the white dwarf. It's about the size of the Earth. White dwarfs are very small. The big difference in the transit properties is that now the transits are incredibly deep. This particular simulation, something like 70%, but planets can actually be much larger than the white dwarf stars that they orbit. And so transits can be total eclipses where the star light is completely blocked out temporarily. So we don't need precision space-based photometry to detect such a tens of percent to a total disappearance of starlight. We can do this with ground-based surveys or telescopes just fine. The difficulties are all related to white dwarfs being small. They're intrinsically faint. The transit durations are very short, like 1 or 2 minutes. The inclination has to be just like so edge on for this to happen. And the planets have to be on relatively short period orbits as well, because if you move the planet further out, the impact parameter gets bigger and you're quickly not transiting anymore. This last point is a little bit of a pro also, though, because if you detect transits of a white dwarf, it implies that the orbit is small. In order for there to have been any realistic chance of a transit, this is a simulated cumulative distribution of orbital period, assuming, making some basic assumptions about planet distributions, that says that, if you catch a planet transiting a white dwarf, it has a high likelihood, majority chance of having an orbital period less than like 10 hours. So if you were to just stare at a white dwarf that has a planet transiting it for an entire night, there's a very good chance that a transit will occur while you're watching. And so this is why I request full nights of APO time to do follow-up of the most compelling candidate transit systems that I find. Okay, so the time is ripe now for us to be discovering these things because we have new survey data that guides us lets us hone in on what particular white dwarfs may have planets transiting them. The first thing is that we have Gaia data. This plot here shows the known white dwarfs prior to Gaia, and you really see the SDSS footprint there. SDSS obtained a bunch of spectra of white dwarfs. It was really trying to target quasars, but we ended up with tens of thousands of white dwarf spectra, which has been great for the white dwarf community. But now with Gaia, we know pretty much where all the white dwarfs are, down to about 20th magnitude, because they're intrinsically faint. So for us to see them, they have to be very close. They have to have very high parallax signals. So Gaia has delivered us most of the white dwarfs that are reasonably bright for like APO follow-up. And we also are in an era of synoptic time domain surveys from the ground. I've been looking at data from the Zwicky Transient facility to try to identify like snapshot moments when white dwarfs are deeply transited. ZTF has observed the Northern Hemisphere thousands of times over the last few years. It's a great data set for trying to identify these transits. I can estimate the number of transits that might be expected to be in the ZTF data set with a sort of back of the envelope. This is like a Drake equation type of expression. We take the number of white dwarfs that ZTF is observing, multiply by the fraction of those white dwarfs that have close-in planets that have some likelihood of transiting, multiply that by the fraction of the orbital time that the planet is transiting, and then multiply by the number of sort of random snapshots that you've taken, chances that you will observe a transit while it's happening. And if you put in some reasonably optimistic numbers, we might suggest that the ZTF data could contain around 500 deep transit detections. If you put in much more pessimistic numbers, assuming a much smaller planet occurrence rate, maybe there's something like 20 transit signatures in the ZTF data. This is what I want to find. It's really a needle in a haystack problem, though, because ZTF has hundreds of billions of individual star detections that you've got to whittle down to, find these dozens of interesting potential transits. But that's what I'm working on. I've been digging through the detections tables from ZTF and measuring for different light curves of white dwarfs, various metrics of interest. I made this little interactive pandas data frame browser where I can explore how different metrics compare to each other and click on points to plot light curves and look at the raw data in more detail. Here I plot the deepest sigma, that's like the faintest point and the number of error bars away it is from the median brightness in that filter compared to Gaia G magnitudes. And there look like there are a bunch of very deep points here, but they're not all what I'm looking for, right? This is like some sort of cataclysmic variable that has a ton of variability. Okay, well, that's easy to discard. But there's some weird stuff in here too. Here's the ZTF light curve where some of the error bars are just so incredibly small. It's nonsense. There's some digital garbage in the ZTF database. Here's an example, much more what I'm looking for. These are GR and I light curves in the different colors, and there's 2 points here. One blue point that's very deep, but potentially a deep transit. In red, there's another one here. This is what I'm trying to find, and but if I go and look at the image that corresponds to this point, there's a problem there too. These are not flagged artifacts in the ZTF data. There's just some bad data in there. So when it turns out, when you look for a needle in the haystack, there's a lot of sharp hay that you've got to watch out for. But here are a few more examples of nice looking potential transits. And when I look at the ZTF image data for these, they look like real solid detections of a very faint moment. And these are some of the objects that I followed up with the high-speed agile frame transfer CCD on the APO 3.5 meter. And so you can see a few animations here. It's almost eerie to watch stars just completely disappear off the sky. Some nights are a little noisier than others, but they just kind of wink out of existence like an opposite nova. You look and all of a sudden a star is completely gone. This is exactly what I'm trying to find, and APO has been helping me measure the durations and details of these. Unfortunately, there's still some ambiguity about whether these are caused by planets transiting white dwarfs or potentially another white dwarf eclipsing in a binary system, or a brown dwarf eclipsing in a binary system. And we can test those by obtaining radial velocity measurements. I've been getting some disk spectra lately, and possibly Cosmos in the future, to put upper limits on masses for these objects. So rule out that they're stars. Don't have compelling results from that yet, just moved on to that phase of the project recently. And I'm also trying to do some forced ZTF photometry to identify when a transit was just completely below the detection threshold of ZTF. So far, I've been looking through the detections table that only tells if there's enough light to be registered as a star still, but like in these examples, a lot of times it's so faint you won't detect it. So I'm running out of time. If you're interested in this sort of thing, there's been a few papers related to this area that I've contributed to from collaborators, some interesting new systems of planetesimals eclipsing white dwarfs from Zach van der Bosch. Joseph Goodry found some more examples of systems like this. And then recently, Jan van Rostel published this paper about a brown dwarf that eclipses a white dwarf that was found in the ZTF data. So check those out if you're interested. And just want to thank you for listening, and thanks APO for all the great data.
Okay, any quick questions? I'll start with one. My question is, how long are the eclipses? Because based on the, if they're a couple of minutes, they're not going to be other white dwarfs, right? It's probably low mass stars or brown dwarfs.
Yeah, in some cases, yeah, they're long enough that they suggest that they are not planets for what I'm finding. So I'm doing follow-up to characterize all of these systems. So, hopefully a planet that'll be a compelling paper on its own. But at the end of this effort, I'm going to publish the characteristics of all the binary systems that I uncovered during this work.
Any questions? Yeah, Nancy, go ahead.
Yeah, thanks, Keaton. That was great. Is there a particular filter that you favor for these observations, and or what's the advantage to using a whole bunch of filters?
I have been using the BG40 filter, which just it's a very broadband filter, lets in a bunch of light. I want just high signal measurements. It has a red cutoff that keeps sky noise from being a big problem. But basically, I want as much light as I can so I can keep these exposure times as short as possible and potentially resolve the shapes of the egress and ingress. But I want my exposure times to be less than a minute. That's the most important thing. So just lots of light. And the great thing about Agile is that no overhead between exposures. I don't want to spin a filter wheel, anything, every once in a while Agile, I like the rotation wheel hangs up and I maybe lose 2 minutes of data and I stress did the eclipse happen then? Did the transit happen right at that time? So yeah, just trying to keep as little overhead as possible.
Thanks, Keaton. So let's continue the discussion on Slack. And